So welcome everybody. It's a real pleasure being here as one of the EuroPLEx Fellows. And in this presentation today, I will talk to you about my second project on B physics from a combination of static and relativistic results. So as we all know, treating the B quark is a very challenging task, and pushing to the B sector is very complex. And in principle, we might think about treating the B quark in analogy with the lighter flavors, but in practice, this is not feasible because we face two major problems. So first of all, we have the so-called two-scale problems, which basically consist in fitting on our lattices both the pion scale and the B quark scale. And then we also face very large cutoff effects due to the heaviness of the B quark. And in parallel, we might think about extrapolation strategies by simulating at several values of the relativistic masses below the B quark scale and then extrapolate to the B quark scale. But again, this is very complicated, and this kind of extrapolation are very hard to control. So basically, what we typically do in our community is to eventually use some kind of effective field theory in order to tackle B physics. And in this particular work, in this project, our effective field theory of choice is the heavy quark effective theory, which basically gives us access to low energy physics, provided that the energy scale involved satisfies some constraint. And HQET is a very interesting theory because it is a renormalizable theory, and continuum limit can be taken. But however, the required 1 over NB correction are very challenging to be determined. So the main idea of our project is basically something that was proposed some times ago already, and it basically consists in combining a set of static data, a set of in the infinite mass limit, a set of relativistic data with masses lighter than the B quark scale, and then interpolate between the two sets of data as I'm showing here in this sketch. But in practice, this strategy in this naive formulation is not really feasible because, again, we face some problems which have to be solved. And in particular, what we need is we have basically a non-trivial renormalization plus and matching in the static approximation. And in addition, we also require a non-perturbative treatment of the B quark scale. However, this idea of interpolating between the static and relativistic results can be performed if we work with a clever workaround, which basically consists in building quantities where we cancel completely the normalization and matching coefficient from our theory. So before showing you the details of our strategy, let me briefly go back to the static theory just to give you the insight of the static theory. So we begin with a static action where d0 is the static data propagator, and if we compute the static energies from this Lagrangian, we end up with this static energy which diverges as the continuum limit is taken. So if we now consider the heavy quark effective theory expansion of our energies, we see that in addition to the static term, we have two additional pieces, this delta m and this MB finite, which are basically the renormalization term, delta m, which cancel the divergences, and the matching coefficient which is extracted from the matching between QCD and HQET. And similarly, if we now look at the heavy light vector currents, what we have, as shown here, is that the vector currents in the static limit, again, they have this multiplicative matching coefficient CV and this the renormalization constant. And in particular, what happens is that the matching coefficient is log divergent as MB goes to infinite. So basically, given this slide, the clever workaround in order to make this interpolation between static and relativistic data work is to basically to build suitable ratios in such a way that the renormalization and matching coefficient cancel out completely. And in particular, this strategy becomes particularly powerful if we combine it with the step scaling in volume. And this is exactly what I'm showing here in this plot, where I'm showing you all the volumes that are involved in our computation. So basically, we start from the volume L1 of 0.5 Fermi, where we can truly reach the relativistic B quark scale. And then through step scaling, we evolve up to the large volume, where we are going to use CLS ensemble with volume between 4 and 5 Fermi. And Therefore, in the next of this talk, I'm going to basically introduce this major object, this rho and sigma, which are the step scaling function connecting the volume L2 to LCLS and L1 to L2, respectively. Okay, so given this preliminary motivation, in the next of the talk, I'm basically going to introduce you the theoretical strategy specifically designed for all these observables, for the big quark mass, for the leptonic decays FB star and FB, and then we will try to extend this strategy to the semi-leptonic form factors. And then finally, I will show you some numerical results on the big quark mass and on the leptonic decays. So starting from the big quark mass, as I was saying, in the small volume L1 of 0.5 Fermi, we can really reach the relativistic scale, and therefore what we do is to extract the RGI quark mass from the PCSE masses, and then we use the non-perturbative running factor HL0 computed by the alpha collaboration in order to obtain the RGI mass. Then, once we have this quantity, what we do is to build this ratio here, this pi ham, which is nothing but the ratio between the pseudoscalar mass computed in the very same volume over the RGI mass. And this is basically used to convert the pseudoscalar masses to the RGI scheme. Now that we basically have this quantity, what we need is simply to connect the pseudoscalar mass in the small volume L1 to the large volume in a clever way. And by clever, I mean that we have to make sure that we properly cancel all the divergences that I was mentioning before arising from the static theory. And this is exactly what I'm showing here with this series of subtraction, where, as you can see, each term cancels completely, and eventually we recover the equalities. So now, if we now rearrange this equation and we make it dimensionless with the volume L2, we end up with this master equation here, which is the one that we use to extract through the step scaling techniques our RGI quark mass in here. And again, as you can see, all the terms cancel completely, and then on the denominator we have this factor that converts the pseudoscalar masses to the RGI masses. This very same equation can be written in an even more compact way by introducing the step scaling function rho and sigma as the differences of the masses computed in the different volumes, and we basically recover the big quark mass when we use as physical input the flavor average combination between the B and the BS meson. In here, with this Y, YB, Y2, and Y1, I am denoting the target point of the big quark scale in the different volumes. And once we define our physical inputs, the other point, Y2 and Y1, at which we are going to interpolate the relativistic and the static data, can be computed recursively by simply subtracting to the physical input the value of the previously computed step scaling function. Okay, this same strategy can be also extended to the vector decay constant. So if we consider a vector meson decay constant, which is extracted from this matrix element, we have this heavy quark expansion that we see here. And in the finite volume, where again we reach the relativistic big quark, we can extract the matrix element that mediates the transition that we want to study by simply taking the ratio between the bulk to boundary over the boundary to boundary correlators. Now, if we recall from the previous slides where I was talking about the static theory, in the vector currents, we have multiplicative renormalization and matching, and we want somehow to get rid of these quantities, and this can be done by simply taking the logarithm of our vector matrix element in such a way that we recover a similar pattern as we had in the case of the mass. So now, what we simply have to do is to connect the finite volume matrix element in L1 with the large volume, again in such a way that the additive divergences are cancelled out, and we again end up with this equation that connects the finite volume matrix element to the other volumes by always cancelling the divergences. If we now again rearrange this equation and we make this term explicitly, the large volume explicit, we end up with this final master equation here, where which basically tells us that the large volume decay constant, either the pseudoscalar or the vector, is nothing but the value of the matrix element extracted in the finite volume L1 plus the two-step scaling function, and here I report again the definition of the step scaling function as the differences between the matrix element computed in the two volumes. To conclude the theoretical part of this talk, let me also mention the extension of our strategy to the extraction of semi-leptonic form factor. So if we limit ourselves to the rest frame of the B meson, we can have this form factor decomposition for the relevant matrix element, where we introduce this H-perp form factor. If we now look at the heavy quark effective theory expansion of this form factor, again, we end up with this matching coefficient and with this renormalization constant, which are somehow problematic to compute, as they basically present some log divergences in the B quark mass. So again, the idea is to build appropriate ratios in such a way that we cancel these problematic matching and renormalization quantities, and we basically can build this kind of ratio by simply using some reference observables, some reference scale, in such a way that we eventually recover the only 1/m correction without log terms. And it turns out that it can be particularly useful in this case, to select as reference scale the vector decay constant step scaling function that we introduced previously, in such a way that we can connect the previous determination of fb star to the form factor, and we eventually end up with this master equation here to extract the form factor in the large volume. And the interesting fact of this strategy is that in such a way, we basically push the computation of the form factors in the large volume only. And so basically, this formula can be used once we have computed the step scaling function for fb star. Okay, this concludes my theoretical introduction. So let me now go to some numerical results. And I will start from showing you the results for the B quark mass determination. Again, I'm showing you here the master equation with the physical input YB, which is the flavor average combination between the B and BS masses. We have the step scaling function rho and sigma, and the conversion factor pi m. And again, I'm showing you the volume involved. Now, let me stop on the ensemble briefly. Let me describe you our setup. So in the large volume, we are using CLS ensemble with 5 value of the lattice spacing and order A improved Wilson fermion with 2+1 flavor. Then, in the finite volume, we are using Schrödinger functional boundary condition projected to the zero topological sector, and we basically have different volumes from around 1 Fermi to 0.5 Fermi. And as you can see, as we go down in volume, we can reach finest lattice spacing, and therefore, as we go down in volume, we manage to eventually arrive at the smaller volume of 0.5 Fermi, where we truly reach the relativistic B quark scale. Now, the first step of the computation is the extraction of the step scaling function between the large volume CLS and the volume L2. However, these two ensembles are computed at an overlap range of the beta and of the quark masses, but they are not simulated at exactly the same values, and therefore small interpolation are required before building the step scaling function. And this is what I'm showing you here in these slides. So on the CLS side, we have the pseudoscalar mass in units of L2 versus the renormalized quark mass, and what we do is basically to select horizontal ranges at which we want to interpolate that we later use to extract the corresponding quark mass. And then when we go to the finite volume, we use the previously determined value of the quark masses to interpolate at the target values, also in the finite volume. Once this small interpolation is performed, we can finally proceed by building the relativistic step scaling function, which are, again, nothing but the difference between the pseudoscalar masses computed in the two volumes. And what I'm showing here is the continuum limit extrapolation of the step scaling function at four different values of the quark masses. The yellow point corresponds to a region around the charm scale, and the purple one corresponds to around 0.3, the B quark mass. And as you can see, the extrapolation is fairly linear with a behavior which is compatible with order A squared. And something else that I want to mention is that as we go to heavier masses, we systematically exclude the coarsest lattice spacing that do not satisfy this constraint here. Okay, the second step is the extraction of the static step scaling function, again in the volume L2 to LCLS. The static step scaling function is defined as the difference of the static energies, and once again here I'm showing you the continuum limit extrapolation of our static step scaling function. Something that I want to mention is that in this computation, we require the improvement coefficient CA stat, but unfortunately, this is not known for the Lucier-Weiss action, and therefore, at the moment, we are using the one-loop computation of CA stat from the Wilson gauge action with 200% error in order to be conservative. Okay, so now that we computed a set of relativistic step scaling function from the charm scale up to 0.3 the big quark mass and a static step scaling function, we can proceed by interpolating our two sets of data, and this is exactly what I'm showing here. So here we have the relativistic step scaling function around the charm scale and going heavier. Here we have the static data, and this is the point at which we interpolate in order to extract the step scaling function at the target scale. And how do we determine this target scale? Well, this is simply given by the physical input in this step between L2 to LCLS, which is nothing but the flavor average combination between the B and the BS meson. So if we now go back to our original strategy, we just computed this step scaling function between L2 and LCLS, and we can now move to the next step, which is the extraction of sigma between L1 and L2. This step is easier because the ensemble L1 and L2 have been already generated with the same value of the big quark mass and at the same target betas and at the same beta, sorry, and therefore we can proceed directly with the extraction of the step scaling function. And what you see here on the left is the continuum limit extrapolation of the step scaling function up to 0.5 the big quark mass, where again we exclude the coarser lattice spacing as we go heavier in masses, while on the right I'm showing you the continuum limit extrapolation of the static step scaling function, where this time we are using two different static actions, HIP1 and HIP2, to constrain the results in the continuum. Again, we have the static data, we have the relativistic data, we can simply interpolate among the two at the target big quark scale Y2, which is now determined by the physical input minus the previously determined step scaling function connecting L2 to LCLS. If you now go back to the original strategy, this is what we computed, and we can now move to the final computation of L1 in a full QCD setup. So if you remember, in this volume, we have to compute this ratio, this pi m, which is the ratio between the pseudoscalar masses and the RGI quark mass. And in here, on the left, I'm showing you the continuum limit extrapolation at different value of the masses between 0.9 and 1.1 the big quark mass. And as you can see, the continuum limit extrapolation is perfectly flat, even if we have very heavy masses, and this is also thanks to the huge effort in the computation of the improvement coefficient. If we now move to the plot on the right, I'm showing you the interpolation to the target B scale of the continuum limit step scale, of the continuum step scaling function that we extracted from this 4th point, where again, this target point Y1 has been determined by the physical input minus the two other step scaling functions. We now have all the pieces, we can just combine them together, and we can extract our value for the RGI big quark mass. And this is our final results with a 0.9% accuracy. On this pie chart, I'm showing you the major contribution to the variance of our determination, and as you can see, our dominant error source is the non-perturbative running factor HL0. For the sake of comparison with other collaborations, we also computed the big quark mass in the MS bar scheme, and in this case, we have an extra error contribution which is entering the game, which is the error arising from lambda. And finally, in this flag style plot, I'm showing you our final results in blue and how it compares with other determination and with the flag average. Okay, we can now move to the final topic, which is the step scaling function for the FB star decay constant. So again, let me show you the master equation. We have the large volume decay constant extracted from the finite volume 1 plus the contribution of the step scaling function to jump up in volume. And these are the definition of the step scaling function that we introduced previously. So I won't have time to go through the whole computation as I did for the big quark mass. So what I want to show you here is simply the interpolation between the relativistic data and the static data in the volume L1 to L2 and L2 to LCLS. So now, starting from the left, I'm showing you in blue the results for the vector decay constant, while in red, yellowish, we have the results for the pseudoscalar decay constant. And as you can see, in the static limit, we know that we have to recover the same limit as we go to infinite masses. And on the right, on the other hand, I'm showing you the same quantities, again in blue the vector and in red the pseudoscalar decay constant, interpolated between the relativistic set and the static data, again at the target B scale, YB. Something else very interesting that we can study from our setup is the ratio between FB and FB star. And basically, if you want to access the ratio from our step scaling strategy, we have to take the differences of the previously computed step scaling function in all the different volumes. And this is, again, the final formula that we have to implement. Now, as we know, in the static limit, FB and FB star, they share the same static limit. And therefore, when we take the difference in order to interpolate the relativistic and the static data, we know that in the static limit, we have to go to 0 without error. And this strongly constrains our interpolation. And in these two plots here, I'm showing you, again, the interpolation between the relativistic data and the static one for the L1 to L2 step scaling function, while on the right, we have again the relativistic data and the static one for the L2 to LCLS step scaling function. Finally, this is our results extracted from the step scaling, from this master equation here for the step scaling function, and we achieve a 7 per mil accuracy. In order to check our results, we also extracted the ratio from the independent determination of FB star and FB, and as you can see, they nicely agree within error among the two strategies. So finally, to conclude, I want to show you this very scary plot, which is a comparison plot between different determination of the ratio between FB star and FB. And what I'm showing you with this green pentagon is the ratio between FB star over FB, with the blue triangle between FBS star over FBS, and finally, in circle, the quantity that we computed, so the ratio of the flavor average combination between FBS and FB. And this is our results, and now it compares with other determination. Here at the bottom, you can also see our final results for FB star in MEV and for FB, again, the flavor average combination, where we reach around a 2.5% accuracy. And this one here in black is the results taken from the 2+1 flag 21 average. And as you can see, we nicely agree within error with the flag determination. So to conclude, in this talk, I tried to convey you why combining a static data and a relativistic one is a very attractive option to tackle the B sector. And in particular, we performed a fully non-perturbative calculation by the combination of these two data sets while keeping under control the cutoff effects in each step of our computation. Among the improvements, we are currently working on the extraction of CA stat for the Wilson gauge action, and we are planning to assess the systematics by studying different cuts in the fit that we perform, both the fits in the mass and the continuum limit fit. And for the future, we are now planning to include more ensemble in order to extrapolate to the physical point, and we are also planning to extend the analysis to the semi-leptonic form factor, following the strategy that I showed you before. So the take-home message of this talk is basically that this strategy, as I tried to convey, only requires to build some quantities that properly cancel the renormalization and matching coefficients that diverges in the static limit. And in particular, what we computed, these step scaling functions, are continuum quantities. And as a result, they can basically be used with any action and by any collaboration. And what I want to highlight is that specific to the form factors, only the large volume computation is required once the step scaling function between FB star for FB star are known. And yeah, with this I conclude. Thank you.